Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about plate girders. In particular, we will talk about post-critical buckling due to shear, which leads to what is known as tension field action. Before we go further, let's discuss what we have studied in the previous classes. So, we talked about elastic buckling, post-buckling as well as inelastic buckling, where the elastic buckling sigma critical is geometry dependent and sigma y and sigma u, which defines the post buckling as well as the inelastic buckling, is a material property and it is independent of the geometry. So, if the plate is very thick, then the elastic buckling is more. As you can see that there is a shift in sigma critical leading to more elastic buckling and lesser post buckling, the region between sigma critical and sigma y. If the plate is thin, then you have less elastic buckling. As you can see that the sigma critical is very close to the origin and you have more post buckling, that is between sigma critical and sigma y. There is a large distance leading to more post buckling. Now, the capacity of thin plates due to elastic buckling, sigma critical, is given as k into pi square d divided by a square, where k is the elastic buckling coefficient of the plate, d is the flexural rigidity of the plate defined as E into h cube divided by 12 into 1 minus mu square, and a is the width of the plate. So, when we plot the load versus the lateral displacement, which is given as F, you can see that there is no lateral displacement until the load reaches sigma critical. The moment load reaches sigma critical, you can see that there is an increase in the load carrying capacity precisely in a nonlinear fashion. With more F, that is more lateral displacement, there is more increase in capacity, as you can see from the figure on the right hand side. This is given as sigma xa equal to sigma critical plus E into pi square F square by 8a square. So, the average applied compressive stress or actual capacity of the thin plate sigma xa is a combination of sigma critical plus E pi square F square by 8a square, where sigma critical is basically the critical buckling stress of the plate and E pi square F square by 8a square is the additional strength that we get due to post critical buckling. Now, when we plot this one, we get a non-uniform stress distribution due to post critical buckling of the thin plates. You can see in the longitudinal direction, there is a non-linear stress distribution that is taking place across the width of the plate, and there is more load that is carried at the edges due to the tension stiffening that is happening in the transverse direction. And you can see that the non-linearity in the form as described here. So, there is lesser and lesser stresses that are being carried at the middle of the plate. This load distribution has also been studied in the previous classes. Going forward, we need to understand two things. There is two questions need to be answered. Question number 1, where do we adopt this beneficial effect of post-critical buckling of thin plates in practice? Question number 2, how does IS 800-2007 account for post-critical buckling into the design of steel sections? Before we go further, let us understand the dimensions of hot rolled steel sections from a steel factory that are standardized. So, the conventional standard structural steel sections available in IS codes are formed using hot rolling process. What you see is a table for wide parallel flange beams, WPB sections. This is from IS 12778 published in 2004. You can see the section on the right hand side, the flanges are parallel. The depth of the section, the overall depth is given as D, the width of the flange is given as B, the thickness of the flange is given as capital T, and the thickness of the web is given as small t. We also have a root radius which is R, right. Now, why do we have to look into this one? We need to understand what is the maximum depth that this cross section has. So, from this one we can understand that the maximum depth of the cross section is 900 mm that we can get from the parallel flange beams. Now, let us look at another code which is IS 808 published in 1989. This is for medium weight beam, which is ISMB, Indian Standard Medium Beams. You can see that these are all tapered flanges, not parallel flanges. As you can see here, there is a tapering at the flanges and you can see that the flange edges are very thin, and as it goes towards the web, it becomes thicker. And the width of the flange is B, the depth of the section is D, and you can also see an alpha, that is the angle. The T, capital T, is the thickness of the flange. Unfortunately, it is not uniform. See, it is taken at B minus T by 4. which is more or less the mid section at that location across the width of the flange, and it is not uniform, and the thickness of the web is given as small t. We have two radiuses, one is called the root radius r1 and another is the toe radius r2 as shown in the figure on the right hand side. Now the maximum depth here is actually 600 mm. This is for ISMB 600. Now let's look at another cross section, which is ISHP, Indian Standard Heavy Beams. The same nomenclature that we described previously applies here as well, and here also R1 is the root radius and R2 is the toe radius, and the maximum depth of the cross section here is basically 450 mm. Now why do we have to study this? The takeaway here is that the maximum depth of the cross section that we can get from a standardized steel section is basically 900 mm. So the hot hole steel sections in IS codes are limited to 900 mm. What we are trying to say is that the standard HRS sections can be insufficient to meet the higher force demands in steel structures. When such is the case, how do we go about it? The solution is to go for a built-up steel sections. So the commonly adopted forms of built-up steel sections can be, you can take two standardized hot hole steel sections, which is option 1. They are called compounded steel sections. You can put a plate at the top and plate at the bottom, weld it together, or you can even bolt it together and form a compound steel section. Option number 2 is to take plates and then weld them together. There is a top plate which is a top flange and bottom plate which is a bottom flange, and weld it together with a thin web, and you call it as a welded plate girder. Option 3 is to go for a truss girder, as you can see on the picture on the right hand side. The first one, which is 2 or more sections connected appropriately, is uneconomical and does not satisfy the deflection limitations, because deflection is primarily controlled by the depth of the cross section. Here the depth of the cross section remains the same, hence there is not much increase in the moment of inertia and it does not satisfy the deflection limitation. Number 2 is the plate girder. Plate girder has many advantages. Basically, it is a built-up flexural member. Plate girders are fabricated by combining flanges and webs to form a section capable of resisting heavy loads, and it has enhanced bending and shear resistance. The increasing the distance between the flange actually increases the bending resistance because the depth D is increased, while the web area contributes to improved shear capacity. Number 3 is that the applications are widely used in bridges and buildings, particularly where heavy concentrated loads act on long span beams such as dining halls or floor beams in large spaces. Number 3 is the truss girder. The truss girder leads to higher cost of fabrication and erection. There is a problem of vibration and impact. The requirements for higher vertical clearance are more for truss girders, and it also leads to what is known as high maintenance. So option 2 is basically selected in this studies, which is a welded plate girder. So plate girders with thin webs are predominantly governed by stability. Let's recall the difference between laterally unsupported beam as well as a laterally supported beam. So laterally supported beam, basically it's supported at the compression flange on both sides. So they go through vertical displacement and it is governed by strength. Laterally unsupported beams basically are not supported, so they go through a displacement vertically, which is V. They also go through a lateral displacement U, and they also twist, which is gamma, and this is governed by stability. So we can identify the beams as per IS 800-2007 based on web slenderness, which is D by T as well. How do we do so? The design bending strength of a section which is not susceptible to web buckling under shear force before yielding, where D by TW should be less than 67 epsilon, shall be determined according to 8.2.1.2. Basically what they are trying to say is that when D by TW is less than 67 epsilon, which means that web buckling will not take place, it can be designed as a laterally supported beam. And the equation for that is given in 8.2.1.2, which is m sub d equal to beta sub b into z sub p into Fy divided by gamma m naught, where z sub p is the plastic section modulus. Now let's look at the next one. When the flanges are plastic, compact or semi-compact, but the web is susceptible to shear buckling before yielding, D by TW less than 67 epsilon, the design bending strength shall be calculated using one of the following methods. All they are trying to say is that when the D by T ratio is greater than 67 epsilon, it can buckle through shear buckling. That is, before yielding, it can undergo shear buckling. The webs are susceptible in that fashion, and for that, how do we solve the problem? So basically they are saying that it has to be done such that the bending moment and the axial force acting on the section may be assumed to be resisted by flanges only, and the web is designed only to resist shear. Now let's look at the I section, where the area of the flanges is given as A sub f and the thickness is T sub f. The depth of the web is given as D and the thickness of the web is Tw, and the center to center distance between the two flanges is given as D1. Here, when d by Tw less than 67 epsilon, here epsilon is given as root of 250 by Fy, it can be considered as laterally supported and the whole section resists the moment. In the next picture, you can see that it is a thin web when d by Tw is greater than 67 epsilon. Here only the flanges resist the moment, and basically this is plate girders with thin webs, and they are susceptible to what is known as shear buckling. Now let us understand the proportioning dimensions of a plate girder, basically the depth and thickness of a web. See, the depth of a plate girder is influenced by load, headroom clearance, high water levels and transportation constraints. The typical depth to span ratios range from 1 by 6 to 1 by 15 with an average value between 1 by 8 to 1 by 12. Generally, short spans are provided with large depth to span ratios. The optimum depth is to minimize the weight of the girder by using thin and deep webs. In this entire plate girder design, one thing that we need to understand is that the depth is the hero in this entire plate girder design, because the depth leads to the optimization. Higher the depth, more is the load carrying capacity. At the same time, the thickness has to be kept in such a way that it will lead to lesser weight, and if the thickness is more, it could lead to more weight, and if the thickness is very less, it could lead to buckling. But in order to prevent buckling, you have to put stiffeners. So in order to put the stiffeners, you have to design the stiffeners accordingly. And this goes so on and so forth. But the first and fundamental thing is to understand how to arrive at the optimal depth so that the weight of the girder is minimized. However, it isn't always economical for having a very thin web due to increased cost for transportation, erection and stiffener fabrication. So if the moment M is assumed to be resisted entirely by the flanges, then for an I section beam approximately, Mg is given as Fy into B sub F into T sub F into D. And this can be categorized as equation 1, where Mg is the moment carrying capacity of the section, where Fy equal to the design strength of the flanges, B sub F is the width of the flange, T sub F equal to the thickness of the flange, and D is the depth of the web. Now the gross sectional area of the girder is given by A equal to 2 into B sub F into T sub F plus D into Tw. This becomes equation 2. Here T sub W is the thickness of the web. Eliminating Bf and Tf using equation 1, we have A equal to 2m sub z divided by D into Fy plus D into T sub W, which becomes equation 3. Now substituting web slenderness ratio, which is K equal to D by Tw, we have A equal to 2 into mg divided by K into Tw into Fy plus K into Tw square, which becomes equation 4. The optimum value of Tw may be obtained by differentiating equation 4 with respect to T sub W and equating it to 0. When we do so, we differentiate it partially with respect to T sub W and we get the following values, which is 0 equal to minus 2 mg divided by K into Tw square into Fy plus 2 into K into Tw. When we rearrange the terms, we have Tw equal to mg by Fy into K square, the whole power 1/3, which becomes equation 5. A similar exercise can also be carried out using K equal to D by Tw, and equation 3 may be rewritten as A equal to 2 mg divided by D into F sub Y plus D square divided by K, which becomes equation 6. Now, the optimal value of D can be obtained by differentiating equation 6 with respect to D and equating it to 0, similar to what we did for T sub W. So, when we do so, we have 2 into mg divided by D square into Fy equal to 2D divided by K, and D is now given as mg into K divided by Fy, the whole power 1/3, which becomes equation 7. So, after the total girder depth is estimated, the general proportions of the girder are established for the maximum shear and bending moment. The shear is assumed to be taken up by the web and the moment by the flanges. Now, let us talk about the types of buckling in thin webs. Now, why did we come into thin webs? Thin webs are basically to optimize the cross-section geometry. We want the flanges to be as far apart as possible, and doing so, we increase the depth of the web. When we increase the depth of the web, the weight of the cross section increases. So we have to reduce the thickness of the web. When we reduce the thickness of the web, we will have some kind of a buckling, and there are several types of buckling that will occur in thin webs. So in order to optimize the cross section, it is very important for us to understand the different types of buckling that will occur in thin webs and how to avoid them, or how to take advantage of post-critical buckling stress due to thin webs. So this is our objective in this slide. So now let us look at the different types of buckling. The first buckling is called shear buckling or shear diagonal buckling, which is a critical aspect for plate girders with slender webs. Now it occurs under shear stress where diagonal compression causes instability. The picture that you see below is basically the test that I carried out during my graduate studies at National University of Singapore. You can see the reference under the guidance of Professor Shanmugam and Professor Devendran. And I carried out several tests here to understand the tension field action in plate girders which are curved or horizontally curved in nature. The one you see is basically a horizontally curved girder whose curvature is basically 45. So you can see that curvature 45, and W200 represents the thickness of the web, which is 2 mm. And you can see that the diagonal tension field band that happens on the left side of the girder as well as on the right side of the girder, as you can see. The next one that we need to talk is the bending or the longitudinal buckling, also known as lateral torsional buckling, which takes place in plate girders. Here in this case, the lateral torsional buckling was arrested by keeping what is known as some kind of a tie rods, which you don't see in this picture here. Basically, they are hidden behind this picture. There are two tie rods, one tie rod at the top and one tie rod at the bottom, where the load is being applied in order to prevent the twisting at the application of the loads. As well as you can see on the left hand side, there is a secondary girder which may not be obvious. You can see that there is a secondary girder and I section which is shown on the left side as well as on the right side to prevent twisting at the support conditions. And all these things are designed to take into account or to prevent lateral torsional buckling, which is very much in case of a curved girder. And to prevent twisting, we have the secondary girders at the two support conditions as well as the tie rods at the application of the load, so that the focus of this entire experiment is only on the shear buckling of the web. So the lateral torsional buckling occurs when the web buckles due to bending moment. However, in this case, it has been largely prevented. The next one is the bearing or vertical buckling or web buckling. It is also prevented in this condition and it results from excessive local stress on the web. So to understand clearly, there are three types of buckling in thin webs. One is called the diagonal or the shear buckling. The next one is the bending or the lateral torsional buckling. The third one is the bearing or the web buckling. There are also high shear zones that need to be taken into consideration. Typically, these are found near the supports and around the neutral axis where the shear forces are concentrated. This is basically due to principal stresses that are inclined to the longitudinal axis of the girder. So when we take a deeper look at the right side of the picture, which is basically highlighted one and it is color coded, as you can see that one is basically causing compression in the diagonal direction and one is causing tension in the other direction, which is 90 degree apart. So this is the state of stress within the web plate. The diagonal tension typically causes no major issue because tension is very much helpful for taking more load. However, the diagonal compression leads to web buckling, which is undesirable. Now, if you look at a plate girder, the load is applied at the center. This is a simply supported plate girder with a concentrated load at midspan. The stiffeners are placed at critical zones to resist shear buckling. So, at the place where the concentrated load is taking place, you have a load bearing stiffener. And at the ends where a concentrated load happens at the supports on the left side as well as on the right side, we have two stiffeners and basically both of them together are called the end post. And there are a lot of intermediate transverse stiffeners whose primary objective is to provide stiffness to the web and it does not make a contact with the flanges. As you can see that there is a gap at the top and at the bottom of the intermediate transverse stiffeners, simply to ensure that it does not buckle accidentally when the top flange gets in touch with the intermediate transverse stiffeners. So it has been designed such that they are not fully connected with the top and bottom flange. There is a gap at the top as well as at the bottom, primarily because the objective of providing intermediate transverse stiffeners is to stiffen the web, not for anything else. Basically, the plate girder with slender webs carry higher loads even after the web plate reaches the critical stress due to what is known as post-critical buckling strength. We have described the post-critical buckling strength in adequate detail in the previous classes, but here we are taking an example of how that can be applied. So the shear buckling strength of the web is basically addition of two factors. One is V critical plus VTF. So V ultimate is equal to V critical plus VTF. From elastic critical stress of plate under shear loading, V critical is given as shear force corresponding to the web buckling, which is equal to AV, which is the shear area multiplied by the elastic critical buckling stress due to shear, which is tau critical into E. So this AV can be written as D into TW into tau critical E. Here, the elastic critical buckling stress of a plate under shear loading is defined as kV into pi square E divided by 12 into 1 minus mu square into D by TW the whole square. Here K sub V is the shear buckling coefficient and D by TW is the plate slenderness, which is depth of the plate divided by thickness of the web. And we have described this adequately. E is the modulus of elasticity 2 into 10 power 5 MPa and mu is the Poisson's ratio. So the VTF is something that we need to figure out. And what is VTF? So what contributes to load carrying capacity after critical buckling stress? It is the resistance to shear buckling after critical buckling stress. So what you see in this picture is basically the formation of tension field band after reaching the ultimate. So you can see that the VTF is the total shear at failure and there is a formation of hinges at the top flange as well as at the bottom flange. So there is a compression flange, there is a tension flange and we have a shear force acting downwards due to the application of load, which is VTF, and there is a reaction at the support which is acting upwards due to the support reaction, which is VTF. And after buckling, the vertical shear is resisted by a combination of two things. One is the formation of tension band due to post critical buckling. You can see the yield zone that takes place, which is also known as the tension band. Next one, we need to understand the distance between the hinges or the formation of plastic hinges. At the bottom, it is S sub T and at the top it is S sub C, which is the distance from the support to the formation of the plastic hinge in the compression zone is known as S sub C. Similar thing that is happening at the tension zone is also known as S sub T. So S sub C and S sub T are the anchorage lengths of the tension field. And the next one, basically the combination is a formation of plastic hinges within the flanges. The contribution to resist vertical shear due to formation of plastic hinges depends upon the plastic moment capacity and the stiffness of the flanges. The plastic moment capacity is directly related to the thickness of the flange. Thicker the flange, more is the possibility to develop plastic hinges and more is the contribution from B, which is the formation of plastic hinges within the flanges and the stiffness of the flange. Now let us look into formation of tension band due to post-critical buckling. The post-critical buckling due to tension field action can be pictorially described as shown here, which is the formation of tension band. You can see that there is a tension band that is happening here. This is basically in the diagonal direction. So here we need to look at what is known as the tension model. The web within each panel of the girder acts as an inclined tie akin to the function of truss post, basically a Pratt truss. So if you look at the right hand side, you can see the formation of tension field band in individual sub panels. This is due to the appropriate position of the transverse stiffener. When the transverse stiffeners are positioned such that the distance between the transverse stiffeners is equal to the depth of the girder, you get the maximum benefit of tension field action. And you can see that as long as the panel is square, you can get more capacity, as you can see. This is equivalent to what is known as an end truss. As you can see that there is an end truss here. The cord here is basically the tension band that is taking place. You can see that the arrow marks are away and the compression band is basically kept empty because the compression does not take any load and the vertical stiffeners acts as a post. So the post-critical buckling behavior can be described as the web in the stiffened plate girder may continue to support loads well beyond the buckling point due to the redistribution of stresses after initial buckling. Proper placement of stiffeners, which I have described previously, basically the spacing between the stiffeners should be such that it is equal to the depth of the girder, enables the web to take tension and avoid excessive compressive deformations, providing substantial post-buckling strength. So the tension field action. So when the web starts buckling, it loses the ability to support diagonal compression, which is transferred to the transverse stiffeners and the flanges. The transverse stiffness resists the vertical component of the diagonal compression and the flanges resist the horizontal component of the diagonal compression. The web only needs to resist diagonal tension after the initial buckling occurs, similar to a Pratt rest where the web acts as the inclined ties and the flanges and stiffness support compression and tension components. So, the tension field action increases the shear strength of the girder after buckling. Let us understand the significance of post-critical buckling of plate girder through a short video. What you can see here is basically a plate girder with web openings. It is also an horizontally curved plate girder. You can see C45 describes the curvature 45 degrees and it is being tested, and you can see, right, the supports at the two conditions are shown here. They are simple supports marked in yellow color on the left and the right side, and the loading is marked in a red color circle at the top where a concentrated load is applied. You can see that it is all connected with a lot of strain gauges. This was done almost 20-25 years back. This was done during my stay at NUS by one of my colleagues. I owe this presentation to late Professor N. E. Shanmugam, who was the professor at National University of Singapore and my master's thesis guide. And you can see that when you apply the load displacement plot is slowly increasing with the increasing in load. And for a while there is no changes in the plate girder, but once it reaches say 60 to 70 kilonewton, you can see that there is a visible decrease in the stiffness, and there is a load drop, and there is a formation of tension band both at the left side of the girder as well as the right panel. And it does not stop there, it continues to take load, but the stiffness is not the original stiffness. The load is kept increasing, the formation of bands is increasing. You can see visible fold that is happening as the load is increasing, and then it is slowly plateauing when it reaches close to 100-110 kilonewton, right. The slope is slowly decreasing, but it continues to take load. You can also see the formation of plastic hinges at the left and the right, although not very much visible. You can see there is a huge dip at the location closer to the supports, and it continues to take load, still moves on. You can see that the central deflection is keep on increasing. Now the load is more or less stabilized at 110 kilonewton, if I may say so, or slightly less than that, and you can see that it reaches and keeps on going. Right, then now it has stopped. So you can see that the tension field action has visibly been displayed experimentally by this short video. You can see that at 60 to 70 kilonewton is where the first formation happens. As a result of the first formation of the tension field band, there is an increase in capacity, which means that stage 1 is basically below 60 or 70 kilonewton, where there is elastic critical buckling stress that is taking care of the load. After surpassing or after the formation of tension bands due to shear buckling, then post buckling kicks in, and after 60 or 65 kilonewton, there is an increase in load. There is no failure. It continues to take load, even though it is a thin plate, it continues to take load, and this results in huge formation of tension band on the left side as well as the right side, and it reaches close to 110. So from 60-65 kilonewton to 100 to 110 is the additional capacity that we can get as a result of tension field action, which is visibly displayed in this graph. And you can also see the formation of plastic hinges, although not very much visible, but you can see at the place where the load is applied at the bottom flange, you can see that there is a big curvature, and also at the place where the support is there at the top flange, you can see that there is a lot of displacement, basically hinting at the location of the plastic hinge, both at the left side as well as the right side of the girder. The formation of tension band on the left side of the girder is towards us, and the formation of tension band on the right side is away from us, and this basically is a result of imperfections. When the imperfections are towards us, and the tension field band also happens in that same way. Basically, buckling is sympathetic to initial imperfections, and as a result the buckling formation follows the imperfection trend, which is obvious in this case. The left hand side is towards us and the right hand side is away from us. Now you can see that pictorially it has been represented by this bearing stiffener and the end post, where you can see that the tension band happening here, and here it is on the right hand side, the load is applied on the left hand side, and the entire thing is basically the thing that happens, the girder that is happening on the right hand side. You can see the tension band here, and at the bottom you can see that the shear is happening at the top as well as the bottom, and the tension panel is shown here in the red color arrow marks. And at the top as well as the bottom there is a buckled panel, basically it does not contribute to any load carrying capacity. Now let us look at the methods to increase the resistance to shear buckling of the web. There are several ways you can increase the resistance to shear buckling of the web. We can reduce the depth to thickness ratio, whereas basically the d/t ratio should be smaller, or we can use web stiffeners. The web stiffeners serve two purposes: form panels that increase the shear strength and resist diagonal compression through tension fill action. Here I have to tell you that there are two types of stiffeners. One is called a bearing stiffener, another is called a intermediate transverse stiffener. The one that is used at places where the load is applied and at the support locations are bearing stiffeners. As the name indicates, it bears and there is a contact between the top flange as well as the bottom flange, and there is a load transfer that takes place as a result of the vertical loading that takes place at the concentrated locations. Whereas intermediate transverse stiffeners serve a different purpose. They are stiffeners, but they are very thin, unlike bearing stiffeners which are very thick and beefy. The shear buckling or to provide resistance to the web in order to increase your post buckling reserve capacity such that the diagonal tension band forms. So the web stiffeners here serve two purposes: form panels that increase the shear strength and resist diagonal compression through the tension fill action. Both of here is basically described for intermediate transverse stiffeners. And there are also other stiffeners which is also known as longitudinal stiffener, and that is typically provided when the depth of the girder is very high. When is the depth of the girder very high? The depth of the girder is very high when it exceeds 20 or 25 feet. Usually it is not done in practice because the longitudinal stiffener increases the cost of construction, because the longitudinal stiffener attaching to the web is done manually. It cannot be done using submerged arc welding. So this will increase the cost of the construction, not to mention the residual stresses as a result of the heat affected zone. And you can also see the top flange elements of the plate girder, the top flange as well as the bottom flange and the web plate and the transverse stiffeners that are acting. Now the web stiffeners do not directly resist loads. Their main purpose is to increase the local stiffness of the web, preventing web shear buckling and facilitating tension fill action as I described previously. So this is an actual plate girder. The picture was taken by one of my colleagues. I owe my thanks to Professor Jim Davidson at Auburn University, USA, currently there, but he was my doctoral advisor during my PhD at University of Alabama at Birmingham. This picture was taken at a fabrication yard in Montgomery, Alabama. You can see the top flange plate as well as the bottom flange plate, which is much thicker than the web plate, and you can see the bearing stiffener at several locations and also the intermediate transverse stiffener. As you can see that there is a gap in the intermediate transverse stiffener which is marked in yellow color circles at the top, and the bearing stiffeners are thicker, actually making a contact at the top flange as well as at the bottom flange. And some bearing stiffeners do not have openings or holes for the bolts, and some bearing stiffeners have that. The holes are primarily given for cross frames, which is very much necessary, especially for curved girders as well as for regular girders, in order to provide the lateral stability for the entire section. And you can also see that it may not be very visible. There is a triangular opening at the bottom. The triangular opening at the bottom is primarily given such that the water does not stagnate, because these plate girders are typically kept at open conditions. When a rain comes, the water should not stagnate at that location, causing pitted corrosion. So there has to be a way to reduce the water content or accumulation of moisture by providing a small triangular opening at the bottom, which is actually indicated by an yellow color circle at the bottom of the intermediate transverse stiffeners. simply to ensure. It is also given for bearing stiffness as well, which is marked by the blue color circle at the bottom of the bearing stiffener, simply to ensure that there is a passage of air, and when air is going through that opening, it will also absorb the moisture, so that there is no pitted corrosion or possibility of pitted corrosion that takes place against this one. So the structure comes for a much longer period, and it is simply a protection against corrosion. So the intermediate transverse stiffeners, these have minimal cross-sectional requirements, as they mainly serve to increase stiffness, not directly to resist shear. So before web buckling, the intermediate transverse do not resist load, so they are just kept quiet at that location. However, after web buckling, they take up the compressive load due to diagonal tension. The shear capacity of the web is enhanced with properly spaced stiffeners, which allow the girder to resist additional shear after web buckling. I have described this in the previous slides as well. The shear capacity of the web can be enhanced when the spacing between the stiffeners is equal to or less than the depth of the girder, where it is a square panel or slightly lesser than that. Then you tend to have more load carrying capacity or more post buckling reserve capacity compared to ones that have a larger spacing between the two transverse stiffeners. So bearing stiffeners, as the name indicates, they are bearing. The stiffeners are placed at points of concentrated load to protect the web from direct compressive loads, and this is something that we have described previously as well. They are designed to resist the applied loads at these locations and provide stability to the girder web. The design of bearing stiffeners follows the column behavior. Basically, the combination of bearing stiffeners and a short length of web can be treated as a column with an effective length shorter than the web depth. This is analyzed as any other compression member in the girder. This will be described in the later classes. Thank you very much.